In this lesson, we're going to talk about rational functions, which are in the form of a linear function over a linear function. So we've already talked about reciprocal of a linear function and reciprocal of a quadratic function. Just moving on to our third type of rational function, which we're going to work on in this unit. Now, I will add that in the next lesson, we are going to basically talk about every single type of rational function, but before we do it, we're just going to focus on linear over linear. Okay, so there's one thing that we really haven't talked about very much, which is the horizontal asymptote. So when we talk about reciprocal linear and reciprocal of quadratic functions, we said that the horizontal asymptote is y equals 0. Okay, now I really want to emphasize it's not always y equals 0. And we're going to take a look at how we can determine the equation of the horizontal asymptote when we're given any rational function. Now, before we talk about horizontal asymptotes, we're going to review some other key features we need to find for a rational function. For example, the x-intercept. How do you find the x-intercept? Let f of x equals 0 and solve. Okay, you let f of x equals 0, basically what you did in grade 9, which is let y equals 0, and you have that equation. If there are solutions to the equation, then you have some x-intercepts. Now, in the previous rational functions, the reciprocal linear, reciprocal quadratic, there were no solutions after you let f of x equals 0, and that's why those functions had no x-intercepts. How do you find the y-intercept? Evaluate f of 0. Okay, so whatever f of 0 is, that's going to correspond to your y-intercept. How do you find vertical asymptotes? Find zeros of denominator. Okay, find the zeros of the denominator, and the real zeros of the denominator will correspond to the vertical asymptotes. Okay, how do you find the horizontal asymptote? So I'm actually going to leave this blank empty because we are going to answer that question in a few minutes, but that's what we're tackling. Okay, we have strategies to find the x-intercept, the y-intercept, and the vertical asymptote, but we have yet to really discuss a strategy for horizontal asymptotes. So what we've been doing so far, one of the strategies to find the equation of the horizontal asymptote is to build a table. Okay, solve for it numerically. So you have a function f of x, and then you just let x values of x be larger and larger and larger negative values, and then that will tell you what happens as x approaches negative infinity. And this table here will tell you what happens to f of x as x approaches positive infinity. Okay, so you know what? Let's fill the table. Let me set up 5x plus 3 over x minus 4. Okay, so this is about 4.7785. 77885. Okay, this will be 4.97709 negative 10,000. Oops, 1 second. Negative 10,000. 4.9977. Negative 100,000. 4.99977. Negative 1,000,000. 4.99977. Okay, so this table here tells us, hopefully, by the way, you can see a trend here. This table here tells us what happens to f of x as x approaches negative infinity, right? The values of x are becoming larger and larger negative values. So hopefully you see the pattern. We're getting closer and closer and closer to 5. Now, is it 5 from above or 5 from below? Now, since it's slightly, ever so slightly less than 5, we're going to say it's 5 from below. And then we're going to do this table here. So this table, once we fill it in, hopefully we'll be able to establish the same pattern as we did when x was approaching negative infinity. So hopefully we're going to approach some number. It should be pretty or fairly obvious. Okay, so this one on x is 100, it's 5.23958, about 239,958, and then if it's 1,000, 5.02309. If it's 10,000, 5.00230. If it's 100,000, 5.00023. If it's 1 million, oh boy, 5 and then 0.00023. So hopefully, hey, what do you know? These values, f of x is approaching 5. But hopefully you notice that these values are slightly greater than 5. Like ever so slightly greater than 5. They say 5 from above. Okay. Just made that prettier. Okay. So, to be honest with you, I could have told you that it was going to approach 5. Without filling these two tables, I knew by looking at the equation, it was going to approach 5. Alright, I'm going to tell you how I know that. Because there's a rule which we can apply, which will tell us the equation of the horizontal asymptote for any rational function. Okay, so what you have to do is compare the degrees of the numerator and denominator. Because remember, to make up a rational function, the numerator is a polynomial and the denominator is a polynomial. So the degree of the numerator and the degree of the denominator. Once we compare the degrees, you'll know exactly what the equation of horizontal asymptote is. So let's say the degree of the numerator is n and the degree of the denominator is m. If n is less than m, which means the degree of the numerator is less than that of the denominator, you'll get a horizontal asymptote of y equals 0. Now this is what you saw in the previous two lessons when we talked about reciprocal of linear functions and reciprocal of quadratic functions. And that makes sense. It must be y equals 0. Because if the degree of the denominator is greater than that of the numerator, that means this function, the denominator of polynomial, will outgrow the polynomial of the numerator. It will be significantly larger as x becomes larger and larger in magnitude, whether it's a large positive or large negative. The denominator will be significantly larger, which means this quotient will be closer and closer and closer to 0, right? Your numerator is being divided by some, like, so the numerator is significantly smaller than the denominator, so it's approaching 0. Okay. If you want to replace it with real numbers, go ahead and give yourself some examples, but hopefully you can see that if the denominator outgrows the numerator, then it makes sense that the function approaches 0. Okay, now what if there's a tie? What if the degree of the numerator and denominator is the same? Well, if the degree of the numerator and denominator is the same, you actually just study the leading coefficient of the numerator and denominator, and the ratio of the leading coefficients will give you the equation of the horizontal asymptote. And we're going to investigate why that's the case. But you know what? It actually makes sense. Because there's a tie, that means the growth of the two functions is the same. Okay, so we're going to approach some number as opposed to approaching 0. Now, what if the degree of the numerator is greater than that of the denominator? So the numerator outgrows the denominator. Well, if the numerator outgrows the denominator, we're never going to approach anything. That's what you study with polynomials, right? With polynomials, you're never going to approach a number. There are no horizontal asymptotes for polynomials, right? If you can think of this one, n is greater than 5, you could think of x, oops, that's a 1, x cubed over 1, right? There are no horizontal asymptotes for a cubic function because the numerator outgrows the denominator. You're never going to approach anything. Okay, that's why for polynomials you'll see that it's always extending to positive infinity or negative infinity. Okay, so we're going to go back. Okay, so let's summarize. So if the denominator outgrows the numerator, we approach 0. If the numerator outgrows the denominator, then there is absolutely no horizontal asymptote. We're not approaching anything. So what we're going to focus on is the scenario where the degrees are the same, okay? So what we're going to do is we're going to study the function that we studied earlier, okay? 5x plus 3 over x minus 4. All right, so what I'm going to do is I'm going to factor the greatest power of x from the numerator and denominator, okay? So if you do that, you'll get, it looks a little funny. Oops, that's a 1. So you factor greatest power of x, which in this case is just x. And then you cancel out, there's a common factor here. Now this will always happen. Hopefully you see a pattern. This will always happen. There's always going to be a common factor if there's a tie in the degrees, okay? If there's a tie in the degree of the numerator and denominator, like if they're both degree 2, there'd be x squared common factor. If they're both cubics, then there's an x cubed common factor. But in this case, they're both linear, so that's why there's a common factor of x. So anyways, what you're left over after you cancel out common factors is 3 over x and 1 minus 4 over x. So let's see. If x is approaching infinity, okay, if x is approaching infinity, what do you notice here? If x is approaching infinity, 3 over x, what does this become? This term basically becomes 0. What about 4 over x? 4 over x also becomes 0. So you know what? Since these two terms, 3 over x and 4 over x, they're basically 0 as x becomes larger and larger in magnitude, just cover them up. What do you have left over? 5 over 1, which is 5, which makes sense. So that's why we take the ratio or the quotient of the leading coefficients, which will yield the equation of the horizontal asymptote. Okay, so this is a very specific example, but you can really imagine that every single time after you factor out the greatest power of x, you'll be left over with the leading coefficients, and all the other terms will tend to 0, will approach 0 as x becomes larger and larger. Okay, so that's where this rule comes from. Okay, when you factor out the greatest power of x, you'll notice that all that's really left is the leading coefficient, the ratio of the leading coefficients. Okay, and it makes sense that you have the two leading coefficients because there's a tie in the degrees. Okay, so it doesn't make sense to approach 0 because there's a tie in degrees, but at the same time, there should still be an equation of a horizontal asymptote because there is a tie. Okay, so let's refresh our memories here. We have our 3 different scenarios. Okay, so determine the equation of the horizontal asymptote for each function. So for f of x, there's a tie here, so we look at the ratios of the leading coefficient. 4 and 1, so it's y equals 1. Now here, you have a numerator of degree 2 and denominator of degree 1, which means numerator outgrows denominator. You're never going to approach anything as x gets larger. The numerator is larger and larger and larger in comparison to the denominator. So we are not approaching any number. All right, so no horizontal asymptote. For this one, with degree of 1 in the numerator, degree of 2 in the denominator. So denominator outgrows numerator, which means the equation of horizontal asymptote is y equals 0. Okay, as x gets larger and larger, you can sub in values like the table that we generated on the first page. You'll notice that the denominator is significantly larger than the numerator. So it makes sense that this ratio will approach 0. Okay. So try to use your imagination, but if you can't see the relationship of the numbers, then go ahead and plug in values for yourself. Okay, and there's one thing I want to remind you. We talked about this in the very beginning of the unit. We cannot cross vertical asymptotes. Okay, for a rational function, we cannot cross it. But a horizontal asymptote can be crossed. Okay, so how do we check whether we cross a horizontal asymptote? So what you do is you let f of x equals the horizontal asymptote value, or the value that corresponds to the horizontal asymptote. Okay, so let's say if the horizontal asymptote is y equals 1, you let f of x equals 1 and see if it crosses. Okay, it may not cross, but you don't know that until you do the math. Okay, all right, so we're gonna do what we did before. We're gonna graph the rational function, so linear over linear. So let's see, x-intercept. So let f of x equals 0. I'll show the math. And the only reason I'm showing it is because I don't want you to assume that there are no x-intercepts, because it seems like every rational function has no x-intercept. Okay, so if you follow the math, you let f of x equals 0 solve, the x-intercept is 0, which means your y-intercept is also 0. You're intersecting at the origin. The vertical asymptote, that's easy. Look at your denominator, linear factor, x equals 3. Okay, behavior in your vertical asymptote, as x approaches 3 from the right, f of x approaches, as x approaches 3 from the left, f of x approaches. I can look at the equation and tell you the answer, but you know what? I'm going to do what I did before. I'm going to graph it, and we're going to come back to this. As x approaches infinity, f of x approaches. As x approaches negative infinity, f of x approaches. So before I tell you what these two numbers are, I need to know what the horizontal asymptote is. It's not y equals 0, because this is a tying degree of the numerator and denominator. So the leading coefficient is 2, leading coefficient is 1, so 2 over 1, 2. So y equals 2, which means f of x will approach 2. And I don't know if it's from above or below, but we'll answer that once we see the graph. So I'm looking at all these other cells I have to fill in. I'm just going to graph it. Once I have the graph, I'll tell you everything you want to know about the function. Okay? All right. So let's take a look here. The scaling we're going to do with 1, 1, 1, 2, 1, 2, 3. And then the horizontal asymptote y equals 2. X equals 3. There's one thing I have yet to do that I really should do, okay, which is check whether we cross the horizontal asymptote, okay, because like I said, sometimes rational function, it does cross. Now I'm going to tell you a little secret though. Whenever you work with a linear over linear function, it never crosses the horizontal asymptote, okay. I know that as a fact, but since let's assume you didn't know that fact, we'll do the check, okay? So check if HA, the horizontal asymptote, is crossed. Okay, let's check if we cross the horizontal asymptote. So let f of x equal, what is it? F of x equals 2. Okay, so 2 equals 2x over x minus 3. So let's see if we're going to cross the horizontal asymptote. Let's see what's the solution to this equation. 0 equals 6. That means this equation is inconsistent. There's no solution to this equation. So since no solution, therefore the horizontal asymptote is not crossed. Okay, we don't ever touch the horizontal asymptote. So now that I know that fact, I think I'm ready to do this graph. Okay, so guess what? I have to approach from the bottom here, because I can't cross the horizontal asymptote and approach it from above. Okay, so I have to approach from the bottom. Okay, have to do this. Now, since the factor of the denominator is raised to the power 1, the opposite behavior on the other side, it must be positive infinity. Bam. Done. Guess what? I'm ready to fill in the table now. I have the graph. I have everything. So 3 from the right, let's see, that's positive infinity. 3 from the left, that's negative infinity. And behavior infinity, approaching 2 from above, 2 from below. It's very easy once you have the graph. I hope you can appreciate the graph. Domain, x is any real number except for 3. Range, y is any real number except for 2, because the horizontal asymptote is not crossed. Intervals of increase is, if you look at the graph, it's the first branch is decrease, second branch is decrease. So it's never increasing. In fact, it's always decreasing. decreasing, decreasing. When is the slope positive? Now, we haven't talked much about this, but where the slope is positive is same as where it's decreasing. Where the slope is positive is where it's increasing. Okay, because positive slope, if you think of the tangent line, if it's a positive slope, that must mean it's increasing. So these two are the same question. And interval of decrease is the same as where the slope is negative. It's just a different way of asking the same question. So don't be confused when you see that on the test. Where is the function positive? So that's basically the second unit, or the first unit even. Negative infinity to 0, or greater than 3. Whereas a negative 0 to 3. All of these questions, very, very easy once you have the graph. Okay, so if you give you this table, right away give yourself the graph and then come and answer these questions. Okay. All right, I think there are one. Oh, there's two more. All right. So this time won't show as much work. X-intercept is 1, y-intercept 1 as well. Vertical asymptote, x equals a third, so which means as x approaches a third from the left, f of x approaches. As x approaches a third from the right, f of x approaches. And behavior, as x approaches infinity, f of x approaches. As x approaches negative infinity, f of x approaches. Okay, horizontal asymptote, so y equals 1/3, because the degree of the numerator and denominator are both 1. So I look at the ratio of leading coefficient, which means this must be a third, this must be a third. I just don't know if it's above or below. But you know what? Once I get the graph, I will tell you. So, like I said, I already know that the horizontal asymptote is never crossed, but I just have to prove that, okay? I have to prove that fact to you. I don't like to just, tell you that is the case, because you know what? Sometimes I'm wrong. So what I'm going to do is use the general form to prove to you that for linear over linear, it's never, the horizontal asymptote is never crossed. So there are two ways of approaching this question. First way is to basically show you that linear over linear is actually very boring. It's very boring because it's what you did in grade 11. A linear over linear, you can prove that a linear over linear is really obtained by taking a reciprocal of a linear and applying a translation. If you apply a vertical translation to reciprocal linear, you'll get a linear over linear. Okay, so in that sense, once you're able to prove that is the case, then you'll realize that linear over linear should never ever cross the vertical asymptote. Okay, so that's one way of approaching that question, or answering the question. Another way is basically to use algebra and let f of x equals a of c, and you realize that the horizontal asymptote is never crossed. So since I've already opened this conversation, I'm just going to show you. I'm going to prove that a linear over linear is a reciprocal linear with a vertical translation. Oops. There's no C here. I don't need brackets there, but you know what? Since I added it, I'm just going to leave it there. Okay, so this is going to be ACX plus BC plus 1. And this is AX plus B. So I don't know what B and C and A is, but guess what? This is a linear, okay? Because BC plus C is just some coefficient. I don't know what it is. And AC is just some other coefficient. BC plus C is the constant, and AC is the coefficient. So guess what? This is a linear, and this is clearly a linear. Okay, so one way of seeing linear over linear is the fact that it's the reciprocal of linear with the vertical translation. So think about it. Reciprocal linear, let's see. Okay. if you shift, okay, this is just one example, but if you shift the reciprocal of a linear function upwards or downwards, are you ever going to cross the horizontal asymptote? Of course not, okay? Of course not. So that's one way of approaching this problem, all right? Another way is letting f of x equal a over c, which is the equation of the horizontal asymptote. And hopefully we'll prove that this equation has no solutions. And guess what? AD equals BC. So you see the x terms are canceled out. So there is something special to say about it, AD equals BC. But I'll tell you something, if A times D is equal to B times C, then we can say A over B is, oh sorry, let's do B over A. B over A is equal to D over C, okay? If B over A is equal to D over C, that's basically telling you that your linear function, or sorry, your rational function, the numerator and denominator are multiples of one another, okay? So if this is true, if A times D is equal to B times C, then the two factors, the numerator and denominator, are multiples of one another. And that's a very special circumstance, which we'll talk about in the next lesson when we talk about simplifying rational functions. But as you can tell, the x terms are canceled out. So we're basically showing you that the horizontal asymptote is never crossed, okay? Whenever you work with a linear over linear rational function, the horizontal asymptote is never crossed. Okay, so with all that being said, okay, whether you like the first argument better or the second argument better, the point is really consistently made. So that makes my life very easy when I study these functions. So let me just make sure I have everything correct. All right, so let's do this is 1/3 here. All right, and now, the intercepts is 1, so 2/3 1, 2/3 1. Okay, so since it doesn't cross the horizontal asymptote, I know it has to do this. Beautiful. Got the label in the first example, I believe. So y equals f of x, and you can do y equals f of x. Okay, so now that I have this beautiful graph, guess what? I'm going to fill in the whole table. So 1/3, or the vertical asymptote from the left side, is going to be positive infinity. Right side will be negative infinity. 1/3 from below, 1 from above. Hopefully you can appreciate how easy it is once you have the graph. I mean, you're really just looking at a picture and really just copying what you see. So hopefully you don't find that too challenging. And if it is, just get some extra reps and you'll be okay. Where is it increasing? Oh, it's basically increasing everywhere. 1/3 and then 1/3 to infinity. Okay, and I'm just going to copy that because where it's increasing is where the slope is positive. And this is never and never. Where is it positive? Negative infinity to third. 1 to greater than 1. Where is it negative? 1/3 to 1. Okay. Alright, let's do one last example. One more linear over linear. So I know it says remember to check, but like I said, I proved to you earlier that it doesn't cross, so I'm good. X-intercept is 2. You can tell the x-intercept really quickly because you can just look at the numerator. Just study the factor numerator, because if the numerator is 0, then the quotient is going to be 0. So just look at the numerator. When is x minus 2 0? When x is 2. Y-intercept, just basically remove the x's, they're equal 0, so -2. Vertical asymptote, x equals -1. Approach the vertical asymptote from the right, approach the vertical asymptote from the left, and hopefully you can appreciate the similarities between the rational functions. You can always talk about these properties when you're studying a rational function. Okay, you can always talk about asymptotes. Now, whether it exists or not, that's a different story. But you can always ask yourself, is there an asymptote? What's the end behavior? Where's it decreasing, increasing, so forth and so on. Okay, let's see. This is 1. Y equals 1. Sorry, please don't write 1. Y equals 1. It's a it's equation of Horace asymptote. So 1. We don't know if it's above, below, but I will find out very, very soon. So, okay, x-intercept is 2, y-intercept is -2. Plot that, plot that. X equals -1, y equals 1. Okay, cross, cross, cross. Do not cross the Horace asymptote. Do not introduce new x-intercepts. Now, because there is symmetry, because I showed you earlier that this function is reciprocal linear with a vertical translation. So, if this point is here, then that's going to be 3 here. And if this point is here, it's going to be there. Beautiful. Why not? Why not add accuracy to your graph? Alright, I have my beautiful graph. Time to just fill in the blanks. Let's see. 1 from the right, -infinity. 1 from the left, +infinity. As x approaches infinity, 1 from above. Ooh, sorry, 1 from below. Whoops. 1 from below. 1 from above. Domain, any real number except for -1. The range is any real numbers except for 1. Intervals of increase and decrease, so increase, both branches. Increasing, decreasing, never. Copy where it's increasing, that will tell you where the slope is positive. Never for slope is negative, where is it positive? For the first branch and part of the second branch. 2 to infinity, so that means -1 to 2. Whew, okay. So, we talked about reciprocal linear, reciprocal quadratic, and linear over linear. The big focus on this lesson is to work with linear over linear, but also talking about how to make sense of horizontal asymptotes. So hopefully you can reason as to why the horizontal asymptote is what it is. Okay, so in the next lesson we're going to open up the floodgates. We're going to talk about every single rational function, so it's going to be really exciting.